How are you all doing today?
Pretty good.
Doing well.
Well, there was a question I got in email regarding one of the homework problems. So we're going to take a look at that before we jump into the in-class assignment and all that kind of good stuff. So this problem is one that often causes difficulty among the students, and it's really just because it's drawn in a way to purposefully be right. So you're told in the problem statement that it is a single node pair circuit, but it may not be entirely obvious that that's the case. So we're going to verify it for a couple of reasons. So I'm going to start at resistor R1 and just go around and map out this node. So we can see that that is all one node. And doing a similar thing on the bottom. This is all one node. So it is indeed a single node pair circuit. I'm going to label the red node as my bottom node for how I redraw this guy, and the blue node as my top. So we'll start just by drawing a line like so. Might be a little longer than I need, but it'll be okay. I can see that since it's a single node pair circuit, literally everything I have is connected in parallel. So I'm going to start over here on the left-hand side and put in resistor R1, resistor R2. So my current source is what I'm going to do next. And this is where having top and bottom labeled is going to be helpful, because I can see that the current is oriented flowing from the bottom node to the top node, or it's flowing from red to blue through that current source. So this is my direction for IS. Then I have my resistor R3. I have another current source. This time it's a dependent one. This guy is flowing from top to bottom. So this is 0.5 Vx. And I said make it even long enough. This guy is resistor R4. Now, let's see, what else do we need here? So we've got our currents for our current sources defined. So let's look at that voltage Vx. So the positive polarity terminal is connected to the blue or top node. So Vx is going to be like this. And next comes what is, in my opinion, the absolute hardest part of this circuit. So what I'm going to do is I'm going to effectively label what I'll call subnodes. And so this point of interconnection between R1 and R2, I'm going to call subnode A. So that is where R1 and R2 meet on the bottom node. So that means this guy is subnode A. Similarly, let's call this guy here B, where B is the point of interconnection between R2 and the current source on the top. So that's subnode B. Let's call this guy C. So this is the point of interconnection between the bottom terminal of the current source and the resistor R3. call this guy D, where that is the point between R3 and the top node of our dependent current source. And then lastly, we're going to have E, where E is the bottom node of our current source in R4. And the reason that I have labeled these subnodes like this is because it's going to make it really easy to identify where those looping currents I1, 3, 5, or I1 through I5 flow. So for instance, the current I1 flows from B to A through resistor R1. So that means this guy right here is current I1. I2 flows from C to A through a short circuit. So this guy is I2. I3 flows from D to B through the short. So this is I3. I4 flows from E to C through the short. So this is I4. And I5 flows from E to D through the resistor R4. So we'll call this guy over here I5. There we go. So now that my circuit is redrawn, I can write KCL expressions in a little bit easier method. So because this is a single loop circuit, the most important piece of information that I can have is the value of that voltage Vx. And the reason I say that is because that voltage Vx is common to all of the circuit elements. And so if we know that, it's going to make all of our subsequent calculations much easier to figure out. So how I'm going to approach this is I'm going to write a Kirchhoffs current law equation with at my top node, and I'm going to have all of the currents that are leaving the top node as positive and all of the currents that are entering the top node as negative. I'm going to express all of my resistor currents in terms of Vx and the resistor value. So to be very clear about what I'm saying, I'm going to kind of draw in light blue real quick all the currents that I'm about to add together. So I'm going to take this resistor current, this resistor current, this current source current, this resistor current, this current source current, and this resistor current, and add them all together. Set them equal to 0. And I'm going to express all of the resistor currents as a function of that common voltage Vx. So who among you can tell me what the current flowing down through resistor R1 would be in terms of Vx?
Vx over R1.
Yeah, Vx over R1, just using Ohm's law. Nothing remotely difficult about that. So Vx divided by R1 gives me my first term, and we'll do the same thing for the current flowing down through resistor R2. So it's going to be Vx over R2. Since my current source IS is in the opposite direction of what I want, it'll just be negative IS, and then Vx over R3 plus 0.5 Vx plus Vx over R4 equal to 0. And now I have one equation, one unknown, and so I could solve for the value of Vx. So all you guys' numbers are going to be different, so I'm going to leave this entirely symbolic. So I hope at this point that you guys are capable of using the numerical solver on your calculator or something like that and getting a value for Vx. So from this point forward, we will assume that the value of Vx is known. and we'll write equations for all of our currents I1 through I5 from here on out, which is what you're asked to do in the problem. Sound good?
Yes, sir.
All righty, so let's look at current I1. How are we going to express that in terms of Vx?
It still would be Vx over R1.
That's exactly right. So I1 is identical to that light blue current flowing down through resistor R1. So our first equation would be I1, that doesn't look like an I. That's easy enough. And another easy one would be to get a relationship for I5. So how would we write an equation for I5 in terms of Vx?
Vx over R4, right?
So I5 is flowing effectively into the negative polarity terminal, right? So
it'd be negative, yeah. Vx
exactly
over
right. Negative Vx over R4. So we've got 2 of our 5 currents taken care of. Unfortunately, the other 3 are a little bit more difficult. So let me erase these guys right here. And now we're going to have options. So let me explain what I mean by that. I guess I'll use Arch. So in determining the current I2, we can write a Kirchhoffs current law equation at subnode A or subnode C to determine its value. So what I mean by that is we could say that I2 is going to be equal to this current flowing up through resistor R2, as well as this current flowing up through resistor R1, doing KCL at this node, or we could write an equation that says this current flowing down plus this current flowing down is equal to I2 by applying KCL at subnode C. And I've been asked a question before about why we're allowed to write KCL equations at subnode instead of the whole node. And so I'd like to address that really quick. So effectively what we're doing by addressing it, well, I guess let me better explain the issue that we're having here. This current I2 doesn't really flow into or out of the bottom node, right? It's flowing parallel with the node, if you will. So it's not flowing into or out of it. So if we address these as subnodes, effectively what we're having is, some sum of currents is equal to 0 plus some other sum of currents is equal to 0 plus some other sum of currents is equal to 0. 0 plus 0 plus 0 is still equal to 0. And that's why we can break this up into little subnodes. And it's actually a technique that we're going to exploit when we get into nodal analysis, gosh, I want to say on Thursday. So this is a little precursor to that. So let me ask you guys, which do you think is a better option right now based on the information that we know? Applying KCL at subnode A or applying KCL at subnode C in order to determine the value of the current I2?
Subnode A.
Right, subnode A would be better because, let's see. Yeah, subnode A is going to be better just because it's based entirely off of the quantity Vx. Subnode C, let me think about this for a second, yeah. Yeah, so subnode C, this current is pretty easy to take care of. This current is pretty easy to take care of. Oh, well, actually, so the issue that we're going to have there then, I've mislabeled this. That's my fault. So we would have that current, but we would also need to figure out this current flowing through, so into and out of subnode C, which will be in turn this guy plus I4, which we don't know, et cetera, et cetera. So going at subnode A is actually going to make our life significantly easier right now. So that's the route we're going to take. So how can we determine I2 in terms of Vx?
Would you do just KCL at that specific node?
Right, so we're going to do KCL at node A. So I'm simply going to add those two currents that I've labeled in orange together, because the current flowing into that node, which is I2, has to be equal to the sum of the currents flowing out of that node. So now I just need to express those currents labeled in orange in terms of Vx. So how would I express the current flowing up through resistor R1?
Again, it would be negative Vx over R1, right?
Negative Vx, because it's flowing in the opposite direction of the current that we've labeled as I1. So negative Vx over R1, and similarly, the current flowing up through resistor R2 is going to be minus Vx over R2. And that's it. KCL at that subnode there. Oops, and apparently I erased this on accident a minute ago. All right, for I3, what we're going to have to do, we're again going to have options. We can have this current plus this current, where this guy right here is the sum of this current and this current. So we're going to have three terms. Or we're going to have this guy up plus this guy, which is the sum of that guy and that guy. So we're going to have three terms either way, and they're both, I guess you could say they're both equally difficult. So which route would you guys prefer to use? The ones I've done in, I guess that's magenta or something, or the ones I've done in gray?
I did the magenta one.
Okay. So for the magenta one, we have the current flowing. So we're going to have I3 is the current flowing down through resistor R1. So that's Vx over R1. The current flowing down through resistor R2. So that's Vx over R2. And the current flowing down through the branch with the current source. So that's minus Is. And that is sufficient to determine I3. So our last current that we have to deal with, let me erase these gray bits then, is the current I4. And there are multiple ways that we could go about this, but I'm going to kind of get this discussion a little bit shorter and say that we're going to use this guy and this guy. So we're only going to have two terms. If we did it at C, we'd wind up having three terms. Our expression would be larger and, in my opinion, slightly more prone to make simple errors. So the current flowing, let's see, so we're going to have I4 is equal to the current flowing down through resistor R4, which is going to be Vx over R4, as well as the current flowing down through the dependent source, which is simply 1/2 Vx. And now we have figured out how to determine all five of our wanted current quantities in terms of our common voltage Vx, just using really Ohm's law and just a whole bunch of applications of Kirchhoffs current law. Sound good?
Yes, sir.
All right. So hopefully that cleared up the questions I got over the email. In my opinion, redrawing this guy is the hardest part. well, redrawing it maybe isn't that difficult, but making sure that you are coming up with clever ways to apply Kirchhoffs current law might be a little, maybe actually the hardest part. But anyway, all right. So did anybody have any questions regarding the pre-recorded lecture content on either source combination techniques or voltage and current division techniques?
No, sir, not for me.
All right, nobody else is saying much anything, so let's pop on over to the in-class assignment then. All right, so here's our first problem, and it's a bit ungainly looking. So let me ask you guys a question then. I'm going to let you kind of guide this a little bit more so than me just telling you the answers today. How or where do you think we should start with this problem? All right, nobody's saying much of anything, so I'm going to ask you guys a question then, and see if you can figure it out. If I can draw on here. How much current is flowing through this branch? Is there any way that you can figure it out based on the information that I've given you?
There be none, right?
You're correct, but I would like for you to explain why, if at all possible.
So the current would be able to go in but not out, right? Because there's only one, I guess, wire.
Wouldn't that technically be a short?
Yeah.
So anywhere we have a wire is a short circuit. A short circuit means that there's going to be no voltage drop over it, but it doesn't necessarily mean that there's going to be no current flowing through it. So your observation that let's see, how can I put this? There's only one path for the current to flow through means that it has to be zero is, I would say, not the best way to put it. So let's instead use Kirchhoffs current law, okay? So if this current is -2 milliamps, because we know it has to be -2 milliamps, and this current is -2 milliamps because it's the same current that's flowing around through this way, then Kirchhoffs current law tells us that if -2 milliamps is exiting that node to the right and -2 milliamps is coming into that node from the top, then the current entering from the left has to be 0. Is that a fair application of Kirchhoffs current law?
Yes, sir.
Okay. So this guy right here, the question that I get a lot is, what's the purpose of this wire? It really doesn't contribute anything to the circuit. It's just, I don't want this to look like two individual circuits. So it's effectively showing that the right-hand side, this guy, is coupled to the left-hand side. That's all it's really doing. So I just wanted to go over that because I get an awful lot of questions about what's going on with that wire, so I thought that we would address them first. Okay, so let's get down to the logistics of working out this problem. So, we do not yet have enough information to determine Vx directly. And the reason why I say that is because Vx, even though it looks like it's associated with a voltage drop over this dependent current source, could just as easily be the voltage drop over the 10 kilo ohm resistor, because all of the elements on the left-hand side of the circuit are connected in parallel. Is everyone okay with that assessment?
Yes.
So,
Yes, sir.
okay. So if If this is Vx, then Vx is simply going to be whatever this current is, let's call it I 10 kiloohms multiplied by the 10 kiloohm resistor, right? Just using Ohm's law, nothing wild or crazy there. The problem is that that current I 10 kiloohms depends on this voltage Vy in some way, shape, or form. So how are we going to calculate the value of the voltage Vy? Do we need to do any circuit analysis whatsoever? Let's start there.
Can't you just look at that little piece of the circuit on the right to determine it using that -2 milliamp and the 1 kilo ohm resistor?
Right, so just using Ohm's law, you're absolutely right. So there's a fixed amount of current flowing through a resistor, so Vy, the voltage drop over the resistor, should just be the current flowing into the positive polarity terminal times the resistor value itself. So the current that's flowing into the positive polarity terminal is that positive 2 milliamps or negative 2 milliamps?
It would be still negative, right?
Right, it'll still be negative 2 milliamps because the current is flowing into this terminal, which is the one associated with the positive sign. So it'll be negative 2 milliamps times 1 kiloohm is what?
Just 2 volts.
Negative 2 volts.
My bad. Yeah, negative 2 volts.
Alrighty. Nothing particularly crazy there. Okay. So this current of 0.03 Vy is then 0.03 amps per volt times negative 2 volts is negative 60 milliamps, if my math is correct. Right, so I didn't explicitly give you the units on that coefficient, but because I know that it is a voltage controlled current source, the units on that coefficient have to be amps per volt because it's a current source, so it's outputting amps and the controlling variable is voltage. So everybody okay with what I did there?
Yes, sir.
All right, so I don't need this anymore because I can now treat this as just a negative 60 milliamp source because that voltage is fixed. So the situation that I have is I have a 12 milliamp source direction up. 60 milliamp, negative 60 milliamps direction up is the same as, oops, hold on, finger got in the way again. Positive 60 milliamps direction down. And 3.5 milliamps direction down in parallel with that 10 kilo ohm resistor, where I have transposed the physical position of the 3.5 milliamp source and the 10 kilo ohm resistor. So let me ask you guys a question. Is it okay for me to flip and flop things like that when they're in parallel? Can I move their position like that?
Yes.
Yeah, it
Yeah.
shouldn't matter.
Yeah, as long as the voltage drop remains constant over everything, it doesn't matter where they're physically oriented. So if they're in parallel, I can mix and match them as I see fit. So I now see 3 current sources in parallel. So based on the source combination lecture, what should I do here?
You would do Kirchhoffs current law, I think.
So you guys aren't watching lectures, but that's okay, I guess. So whenever I have current sources in parallel, I can simply add them together. So what my goal is to have, I'm going to have a total current source direction, let's see, up. So I have 12 milliamps up, 60 milliamps down, and 3.5 milliamps down. So that's going to look like a single equivalent current, let's call it IEQ, is 12 milliamps direction up minus 60 milliamps direction down. That's why it has a minus sign, minus 3.5 milliamps direction down. So what's 12 minus 60 minus 3.5?
Negative 51.5.
Negative 51.5 milliamps. So I can redraw my circuit. That's my equivalent current source. I don't know why that line got so skewed. Connected to my 10 kilo ohm resistor. And this is my voltage Vx of interest. So what's Vx?
Negative 515 volts.
Right, so just that negative 51.5 milliamps times 10 kilo ohms gives me negative 515. So this guy, this particular problem helped you guys, or its intention was to help you guys apply Kirchhoffs current law as well as do source combination for current sources there. That's something that we're going to be utilizing a lot in this class to make things, simplify things. All right. So this guy, problem 2, asks us to determine the power absorbed by the 47 kilo ohm resistor in the circuit below. So since we want the power absorbed by the 47 kilo ohm resistor, we can determine either this voltage, which I'm going to call V47, and the polarity of the voltage doesn't particularly matter because the power is V squared divided by R. Or we could find this current, which I'm going to call I47, where the direction of the current isn't particularly important either because the power absorbed by the resistor is going to be I squared times R. So if we can determine either of those quantities, we can get our final answer pretty easily. So let's see. This is another situation where we have effectively an independent circuit on the right influencing the behavior of a circuit on the left. So we're going to have to look at the right-hand side first. So how can I determine the value of this voltage Vx in the most efficient way possible?
Can you put those two resistors in series, add them together, and then do Ohm's law?
All right, so what you are suggesting is I have a 5 milliamp current source, 3 kilo ohm and 7 kilo ohm. Looks like a 10 kilo ohm resistor. And then a 2 kilo ohm resistor. So, and then I apply Ohm's law to something. So my question there is, using this line of thought, what happened to Vx?
Well, when I first said that, I thought that it would just like consolidate into that one 10 kilo ohm resistor, but the voltage drop is going to be different on the 3 kilo ohm and 7 kilo ohm, right?
Exactly right.
So then we need to just do the 3 kilo ohm.
And this point, not between that top and this bottom.
Yeah.
Okay. Combine those guys, we run into an issue pretty quickly.
Mm-hmm. So just the 3 kilo ohm then?
So do Ohm's law on the 3 kilo ohm resistor. Okay, well, how are we going to determine how much current flows through the 3 kilo ohm resistor? That's a fair assessment. So this current right here, we'll call it I3. How are we going to figure that out?
Can you use the 5 milliamp current?
What about it? Are you suggesting that all 5 milliamps of that current flows through the 3 kilo ohm resistor?
No, it's going to split.
Okay, so it's going to split. So do we have a circuit analysis technique? I don't know, probably one introduced in the last lecture about current splitting between parallel resistive paths. So among the 26 of you, did any of you guys watch the video I made about
Yes.
current division?
Hello?
Yes.
Yes, it's current division rule.
Current division, great. Okay, wonderful. So the current flowing through the 3 kilo ohm resistor, I3, can be determined using current division. So we have the source current of 5 milliamps. The resistance that we're looking for is the total series resistance of this branch. So that's 1 over 3 kilo ohms plus 7 kilo ohms. And then we're going to divide that by the resistance of the left branch, 1 over 3 kilo ohms plus 7 kilo ohms plus 1 over 2 kilo ohms, the resistance of the right branch. And just for math's sake, because it'll be a little bit easier, this is the same as 5 milliamps times 2 kilo ohms over 10 kilo ohms plus 2 kilo ohms is 10 over 12, 5/6 of a milliamp. So somebody do the math on this guy and make sure I'm right, even though I'm 99% sure I'm right.
That's correct.
Alrighty, so now that we know that current I3, how do we find Vx?
Couldn't you just apply Ohm's law to it?
Right.
Since the current's the same throughout the entire thing? Well, the 3 kilo ohm and the 7 kilo ohm, I bet.
Sure. So 5/6 of a milliamp times 3 kilo ohms is 15/6, right? Which is the same as 2.5 volts.
Correct.
Okay. So now this guy, well, actually, that's the wrong thing, is no longer 0.5 Vx. We could simply write that as 1.25 volts. Is that fair? 1/2 of 2.5 is 1.25.
Yes, sir.
Alrighty, so now we're much closer to determining either this quantity I47 or this quantity V47. So I guess my question to you guys is, which of those two quantities do you want to determine?
I-47.
Okay, so roughly the same amount of steps either way, so that's fine. So I47 is going to be the voltage drop, which we know to be 1.25 volts, divided by the total series resistance seen by this source, right? So how am I going to express that? What's going to go in the denominator of my equation?
The 47 kilo ohm resistor.
All right, so the 47 kilo ohm resistor, that's definitely going to be in there. Is there going to be anything else?
The 100 and the 20 kilo ohm resistors in parallel.
Correct. So that's 100K multiplied by 20K divided by 100K plus 20K. Let me get my calculator out because I can't do that in my head. I get 19.633 milliamps, if I did my math right. Anybody else get something similar?
That's what I got.
Alrighty. And so then the power is going to be what?
I think, wait, sorry. I think it would be microamps, right? 19.633 microamps.
Let me actually put in the coefficients here and let's find out. I just divided by a factor of 10 to the 3. So let's see, 1.25
I
divided
might
by
be completely wrong.
47,000 plus 100,000 times 20,000.
I'm also getting microamps, I think.
You are correct, it is microamps. That's what happens when I do the units in my head instead of explicitly doing them in my calculator. So thank you for that correction. Alrighty. So the power, how are we going to calculate that?
Wouldn't it just be 1.25 times the current that we just calculated?
So 1.25 volts times the current that we just calculated would give us the power supplied, no, the power absorbed by that voltage source. But that's
Oh,
not
my bad.
what we're looking for. We're looking for the power absorbed by the 47 kilo ohm resistor.
Couldn't you just square the volt? Or wait, no, we did current. I squared times the 47,000.
That's exactly right. I squared times R. So 19.633 microamps quantity squared times 47 kilo ohms gives me 18.117 microwatts, which I believe matches my answer. Yep. So we took a path that I wasn't necessarily expecting us to take to do this problem. So I'm going to circle back and we're going to find V47 using the principle of voltage division. Although actually, hold on. So I'll do an example of that here. All right, so problem 3 says we have a circuit. It's a small signal model for a transistor amplifier. If Vs of t is equal to 3 sine 10t and the transconductance of the dependent current source is 4 millisiemens, we're asked to determine the quantity V out. All right, so this current here depends on this value V pi. This value V pi we can determine using voltage division. So V pi is going to be our source voltage, Vs of t, 3 sine 10t volts, multiplied by the resistor that we want, the voltage drop over, 15 kilo ohms, divided by the total series resistance seen by the voltage source. So that's 300 ohms plus 15 kilo ohms. And so that's going to be 50 over 17, 2 that's a crappy looking 2.941 sine 10t volts. That's applying the principle of voltage division. Our current, GM times V pi, is then 4 times 10 to the minus 3. So let's see, so that's giving me my milli. Siemens is an amp per volt multiplied by V pi of 2.941 sine 10t volts. Gives me 11.765 sine 10t milliamps. So this current is what's flowing down there. Just using literally the definition of the transconductance and the voltage there. So my question to you guys is then, how do I go about determining that voltage V out?
Do you combine the 100 kilo ohm and 5 kilo ohm resistors and then use Ohm's law to find your voltage across the parallel circuit?
Absolutely. It's fairly simple at this point, right? So that voltage V out, that open circuit voltage V out that we see on the right hand side, is the same as the voltage drop over the 5 kilo ohm resistor and the same as the voltage drop over the 100 kilo ohm resistor. So the easiest way to determine what that voltage is to combine them and then apply Ohm's law. So we can kind of do all of that in one step, but we do need to make one important note, right? So this current is flowing down, so it's going to be flowing into the negative polarity terminal of our equivalent resistance. Does everybody see that?
Yes.
So this current's flowing down, and it's going to flow up into the negative polarity terminal. So our output voltage V out is going to be negative 11.765 sine 10t milliamps times the parallel combination. So that's 100 kilo ohms times 5 kilo ohms divided by 100 kilo ohms plus 5 kilo ohms times 500 over 105. Negative 56.022 sine 10t volts. All right. Let me take just a moment to look at your web work assignment. Let's see, we're on, should be homework 4 or 5 at this point.
4, I believe.
It's 4.
So let's see, share screen, web work. Homework set 4. Problem 1. Alrighty, so this one tells you it's a single node pair circuit and you're asked to find power, so that's nothing particularly difficult in my opinion. you would just redraw the circuit. Since it's a single node pair circuit, everything's going to be in parallel. You just need to make sure that you get the directions on the currents I1 and I2 correct, and after that it's going to be fairly straightforward. Equivalent resistance problems, nothing particularly crazy here, very similar to what was covered in circuits, or so, not circuits 3, homework set number 3. It's just going to be a little bit tedious on part A. Part B is fairly straightforward. Just notice that one of the resistors is shorted out. That's going to affect some things. Part C we did as an example in class the other day, so that's nothing particularly new. This is just another resistor combination problem, nothing crazy there. This guy here. Let's talk about this one for a moment. Because some students get tripped up with, I guess, what you call the terminology of this problem a little bit. So for part A, you're told that a charging current of 1 amp flows. So let me see if I can copy this image over. Nope, I can't see it. It's all black and messed up. All right. Can't draw on it either. All right. So the charging current effectively means, can you guys see my cursor at all on the screen? All right.
No.
No.
No, sir.
What about now?
Now we can.
Okay.
Yeah.
So the system that we have here is a battery charger charging a battery. Very, very simple. You guys effectively set up this circuit in some shape or form every time you plug your phone into a USB port. So for part A, we're told that a charging current of 1 amp flows. So what that means is that 1 amp is flowing from the battery charger through this resistor R1, the resistor R, into this battery, which is formed by this resistor R2 in series with this voltage source V1. This is what's known as a practical voltage source, and it's something that we're actually going to spend a full lecture talking about in about a week and a half or so. So whenever it asks about, so for part A, the charging current of 1 amp, that should be a fairly straightforward problem because this whole thing is just a simple single loop circuit, right? Where if you know what the current is, and you know what the resistor values R1 and R2 is, and you know the voltage value for Vs and V1, it's going to be fairly straightforward to write a KVL equation around the loop and then solve for the unknown resistor R. So part A is fairly trivial. Part B says that a power of 12 watts is delivered to the battery. Now this is the part that starts tripping students up. What it means is that a total power of 12 watts is delivered to that resistor R2 and that voltage source V1 together. So we have, let's see, the weird Chrome, somebody? Situation where we have let's see. So we have a voltage source like this, R1, R. Everything to the left of those terminals is the battery charger, R2, and then V1 like this. So for part B, the power absorbed by the battery, so P bat, is going to be equal to the power absorbed by resistor R2, which I'm going to write as I squared times R2 plus I times V1, where I is the charging current flowing through the battery that's unknown. So what kind of equation is this guy right here?
Power, like
8th grade math. What kind of equation is that?
Polynomial.
Okay, but it's what order of polynomial?
second order.
So what's a
Maybe.
better what's a better name for a second order polynomial equation?
Quadratic.
Quadratic.
There we go. Pull out your algebra, your old school algebra skills, and solve this simple quadratic equation for the charging current. And then once you have that, it's effectively the exact same problem as part A. You have a single loop circuit and you need to find the value of R. Okay. Now let's go back and look at part C. Part C says there is a voltage of 6.1 volts present at the terminals of the battery. So for part C, we have some known voltage. I think that for me it said it was 6.1 volts right here, right? And again, the goal is to find this value of R, which we can find very easily once we know what I is. So this is part B. For part C, we can write a simple Kirchhoffs voltage law loop around this part of the circuit, right? So we would have negative 6.1 volts plus whatever R2 is times our charging current I plus V1 is equal to 0. And then simply solve for I, and then it's the exact same problem as part A. Everybody see what I'm getting at here? So for this particular problem, you're using a lot of the different relationships that we've used in the course to this point to figure out exactly what's going on. I'm not saying you have to get wildly creative or anything. It's just applying a power relationship to part B and a Kirchhoffs voltage law loop for part C. But the problems are getting a little less, I guess, in my opinion, intuitively obvious. So it might require a little bit more effort on your part. So I'm trying to help you out and kind of explain some of the nuances. So anyway, I'm happy to answer questions about this problem or any of the others as they arise once you guys actually take some time to try to work on them. Let's see. Tomorrow's lecture is going to be on the concept of linearity and superposition. So we might work a couple of quick example problems before we get into the in-class assignment, just because I'm willing to bet that those of you that actually bother watching the lecture may have some questions about how and where we can apply that concept. All right, does anybody else have any questions or anything?
Yeah, can you go back to the in-class assignment? I missed part of it.
Sure.
Thank you.
What part of it did you miss, or do you just need to copy stuff down?
It was the VL part. I just didn't copy everything down.
Okay. So yeah, all I did there was at you guys' suggestion, combined the 100 kilo ohm resistor with the 5 kilo ohm resistor, so that I had a single equivalent resistance, and then use Ohm's law to multiply current times resistance gives me the voltage V out. And the negative sign comes
Okay, thank you.
from the currents flowing into the negative polarity terminal. Any other questions, comments, concerns?
When did you say that this will be posted on Moodle or on YouTube?
This the recording of this when I get around to it, so sometime in the next day or so.
Okay.
So so there's been, I don't know if it's a question per se. So the InClass assignments, I want to be clear about this again, because maybe there's some confusion on this stuff. The InClass assignments are not graded for correctness, nor are they really graded for completeness. I want to see that you guys are making an effort towards them. Now, I know that since I'm working them out, we'll be generous and say with you instead of for you during these sessions. The amount of effort you may be putting into them is probably fairly low, and that's okay. I just want you to be aware that these type of problems will show up on your exams, so it would be in your best interest to actually attempt them yourselves at some point, without me baby stepping you through it if you would like to pass this class. So there's also a selection of old tests that I have made available on the course's Moodle page. I'm not sure if any of you guys have seen that or noticed it yet, so if you give me just a moment, I will show you where they're located, and then we can work some of those problems on the review session, or if you want to get ahead of the game a little bit and look at them early, as long as they are pertinent to a topic that we are covering or have covered recently, I have no problem spending some time in class going over them. So if you go to the course's Moodle page, on the introduction section, doesn't matter if you're on in section 084 or V84, there's a folder here on the right that says old tests. And then there are 2 old exam 1s, 2 old exam 2s, and 1 old exam 3. I want you guys to be aware that this particular exam 3 is a cumulative test, and based on the votes that I saw the other day, unless things have changed drastically, it's looking like our exam 3 will not be cumulative. So I may have to generate some more problems for the sinusoidal steady state portion of the class, but I'll worry about that in roughly a month and a half when we get around to it. So for now, you guys should be focusing on studying on exam 1. So we can look at this guy right here real quick. So let's see what we got. So my exams, typically speaking, are roughly 10 problems of, I don't want to say short answer or whatever, but it's simple relationships and things like that, and then maybe a couple of definitions. So for instance, this problem, the first problem, which of the following expressions allows you to calculate the power absorbed by the resistor based on the current flowing into the positive polarity terminal of voltage? So that's obviously going to be I times V, Ohm's law, I squared times R, and V squared over R, which turns out to be 3 different answers, so that's always a possibility. Then we got a simple definition there. Which of the following expressions relate particular quantities? So power and energy. So energy is the integral of power. Power is the derivative of energy. That's fairly straightforward. This problem, simple calculation problem. Doesn't require a whole lot of setup or anything. It's literally just following the units to get through what you need. Nothing crazy there. Superposition theorem we have yet to cover. A couple of other simple calculation problems. Circuit analysis problems on my tests follow the order in which we cover the material. So this problem is lecture 1 type stuff. Maybe it'll involve some KCL and KBL applications as well, but a generic circuit, and I ask you to calculate some quantity of power, nothing crazy there. Let's see, this is charge and current relationships, power and energy relationships, so still lecture 1 materials, combining resistors, so that's some Ohm's law type stuff. This problem is a KVL problem. This problem looks to be a KCL problem. Maybe current division as well might make it a little easier. Then we get into superposition, et cetera, et cetera. So you can really follow along, like when something seems like one of these problems, they're effectively following the order that I'm covering the stuff in this class. So feel free to ask questions about these problems too, so that we can help you guys understand stuff, because I'm concerned, based on the kind of lack of response I'm getting from you guys during the lectures, that a lot of you are half-assing things and are going to do extraordinarily poorly when we get to the exams. And I would like to curtail that behavior as quickly as possible. So anyway, that's enough ranting out of me for the day. If you guys have any other questions or anything, I'd be happy to answer them. If not, I will see you guys tomorrow morning.